My name is Chris Impey. I'm a professor of astronomy at the University of Arizona, and I want to talk about exoplanets and habitability. All life on Earth is one thing, so we have a biological experiment that started 4 billion years ago, seeing here the tree of life with the last common ancestor at the bottom, and most of the genetic real estate in this chart is in terms of microbes. Plants and animals are just a twig on the tree of life. So we live on a microbial planet. Life has been on the Earth for a long time, so the Earth has been habitable for at least 4 billion years. In fact, the zircon crystals that were found in Western Australia from 4.4 billion years ago seem to have formed in temperate liquid water, so it's possible that life started that early. But Earth has certainly been a habitable planet ever since. For 90% of that time, all forms of life on Earth were microbial, invisible without a microscope. And we also need to know that habitability relates to microbes and their diversity of environments. Here are some of the environments of extremophiles. Extremophiles are microbes that can handle ranges of physical conditions that are not tolerable by humans or most plants or animals. And here we see some of their environments. In terms of physical parameters such as temperature, pH, salinity, and pressure, microbes can handle an enormous range of these physical parameters, whereas plants and animals are limited to a moderate range of these variables. So when we're talking about habitable, the envelope of habitability for microbes is enormous compared to the envelope for plants or animals. And it occupies almost the full range of physical conditions possible on the Earth or even in its interior. The Earth has been habitable, but life has only been on land for 15% of the history of life on Earth. And we think about climate change as a current and pressing issue for humans to solve, but during that time, climate has violently fluctuated. Here we see the history of average temperature of the Earth over the last 15%, the entire time that life has been on the land. And we can see violent fluctuations in temperature that dwarf the recent global warming at human hands, and show that the habitability of the Earth has been through very large range of temperature variations, and yet life has survived these variations. In the world of astronomy, exoplanets have been discovered at a prodigious rate. Here's a timeline of the 35 plus years of exoplanet discovery, showing an almost exponential rate of exoplanet discovery. In fact, the only analogy for that rapidity of discovery is a technology like the cell phone. So an extraordinary rate of progress, and as we speak, over 5,700 exoplanets have been confirmed, with 2 times that number remaining to be confirmed, but almost certain to be real. So the number of exoplanets has gone through the roof in the last 5 to 7 years, primarily due to the Kepler satellite. Exoplanets exist in many different populations, and most of these are not terrestrial planets. The first exoplanets discovered were hot Jupiters, giant planets that have no analog in our solar system, orbiting very close to their stars and very high temperature. We've also found icy worlds and water worlds that are larger than the Earth, Uranus and Neptune size. And then lower in this diagram, the rocky planets, the terrestrial planets, some of which are also very hot. Earth-like planets are a small minority of the real estate of temperature, density, and size of exoplanets. Here is the subset of exoplanets that seem to be habitable. And the standard definition of habitability is, of course, the range of distance from a star where water could be liquid on the surface of a planet. That's modulated by the atmospheric gases, most of which act like greenhouse gases to trap radiation and so raise the surface temperature. But here we see dozens of exoplanets, many of them large gas giants, that are nominally in the habitable zones of their stars, of different spectral types. The ones we think most likely to be habitable in terms of real prospect of biology are, of course, the terrestrial planets, the smaller ones. We know that water is a prerequisite for life, and we think is essential for habitability. And this diagram is a reminder that oceans in the solar system exist elsewhere, and in a number of cases they're larger than the water inventory of the Earth, such as Europa and Ganymede and Enceladus. So Water is essential for life, and we see moons of giant planets that have the ingredients for life. So habitability is a possibility for moons as well as for planets. When we look at how much water we might expect to see on planets, we find that having the inventory of the Earth's amount of water in oceans is not unusual. There are exoplanets in simulations and models, and some in real discoveries, that have 10 times the Earth's oceans, or even 100 times the Earth's oceans. Water as an ingredient for life is widespread throughout the universe. Size is important for habitability too. Earth is a habitable planet, and below about 10% of the mass of the Earth, we have Mars, and Mars is on the edge of habitability. There is probably a hard boundary around 3% of Earth's mass, below which a planet will not retain an atmosphere, will not have the geological activity that's thought to be essential for life developing. Here's the populations of exoplanets extrapolated from Kepler discoveries in the last decades. And we can see that the sum of the Earth and super-Earth planets is 1 in 3 of all stars, having a potentially habitable planet. Astrobiologists think that super-Earths, that is, planets that are a couple of times the size and 5 to 8 times the mass of the Earth, are just as likely to be habitable as Earth-like planets. Earth 2.0, if it's found, is not going to be exactly like Earth 1.0. And it's going to be thousands of trillions of miles away, so it will not relieve us of the obligation to take care of our planet. Here are some potentially habitable exoplanets defined in terms of an Earth Similarity Index, where Earth is the best of all possible worlds, even though it may not actually be the most habitable planet. Mars on this scale is 0.64, and we can see a dozen, now ranging up to 20 exoplanets that are more habitable than Mars and almost as habitable as the Earth. We also remember the habitable real estate of outer solar systems, where moons are, and the fact that there are 100 red dwarf stars for every sun-like star, so most of the habitable real estate is actually around red dwarf stars. Here we put a number on the number of habitable worlds. Wet your finger and put it in some sand, maybe 300 grains of sand, all in the nearby galaxy, hundreds to a few thousand light years away. Each one a world, reminded of the quote by William Blake. Extrapolating to the galaxy, we have 10 or possibly 20 billion habitable worlds in the galaxy, the number of grains of sand in the child's sandpit. If we were to inspect each one of these worlds and take a minute to do so, to see if it had life, it would take 100,000 years to inspect them all. It's a vast amount of habitable real estate. And that's, of course, one galaxy, the Milky Way. There are hundreds of billions of galaxies in the universe, and that projects to 1,000 billion habitable worlds in the universe. A fantastic number. We also should remember that exomoons have not yet been discovered, and they could be habitable. Also, simulations find that exoplanets are often ejected in the early chaotic phase of a solar system. And if those exoplanets are super-Earths, they could hold an atmosphere and have geological heating, and so sustain life even without a parent star, floating through the voids of interstellar space. And there could be just as many nomad planets as regular terrestrial planets. Finally, we can look for biosignatures, which is the evidence for life on another planet. This is work that's going to be done soon, looking for ozone and oxygen in the atmospheres of Earths or super-Earths. James Webb Space Telescope will do this, as will a large generation of 20 and 30 meter telescopes on the ground. This could be the first detection of life beyond Earth, and it could come within the next 5 to 7 years. Another possibility is even to detect technological life by looking for industrial pollutants like nitrous oxide in the atmospheres of exoplanets. So not only is habitability the realm of microbes, habitability, of course, is the realm of advanced creatures with brains and technology like us, and astronomers have ways to detect those forms of life as well. This is the way we can think about habitability in the universe now that we live in the realm of exoplanets.